This lesson is going to be on the product rule, but we're going to start with a minds on the power rule from yesterday. So our question is, at what point on the curve y equals x to the fourth minus 25x plus 2 is the tangent line parallel to this line here? So in order to find that, we would first want to find the derivative of y. So this one's easy to find y prime. So y prime is going to be 4x cubed, if we follow the power rule from yesterday, minus, this would be 1 times 25, so minus 25x to the 0, which is 1, so it's just going to be 4x cubed minus 25. Okay, now we want the tangent to be parallel to this line, which means we want the slope of the tangent to be the same as the slope of this line. This line is given to us in scalar or standard form. To know the slope, we could put it into y equals mx plus b, and we get y equals 7x minus 2, meaning the slope of this line is 7. So we want to know where the slope of the tangent to this curve is also 7. So we can sub 7 in here. And then solve for x. And x is only in one place in the equation, so we can just use regular solving equations here. Add 25 to both sides. 25 and 7 is 32. Divide by 4. X cubed equals 8. And then if we cube root both sides, we would get that x was equal to 2. So the slope of the tangent to that curve is going to be 7 when x is 2, but they want the point, not just the x value. So if we know x is 2, we can find the y value that goes with x being 2 on the curve by using the equation and subbing in 2 for x. And we'll get a y value here of 16 minus 50 plus 2, negative 32. So then we can make a concluding statement that therefore the curve y equals x to the fourth minus 25x plus 2 is parallel to the line 7x minus y minus 2 equals 0 at the point 2, negative 32. Okay, so there's kind of an application question from the power rule, what we did yesterday. So we're going to move on to the product rule. So today we're going to learn to find the derivative of the product of two functions, so two functions multiplied together. And we're starting to learn how to common factor to write final answers in simplified factored form, which will be really important when we learn the chain rule in a few days. And third, we're going to see that sometimes it's easier to expand and use the power rule rather than using the product rule. So once we learn the product rule, it will allow us to figure out the derivative of a function like f at x is x to the fourth plus 3x squared minus 7x times 4x squared plus x minus 12. So we could use the product rule because it's the product of one function times another function once we learn it. So it'd be common to think, so if we were going to guess what the product rule was, it would be common to think that it would just be the derivative of one of the functions times the derivative of the other one. But we can see that that's not true with a simple counter example. So if we have h at x equals x to the fourth times x cubed, and our guess was that h prime at x, that's our guess, would just be the derivative of the first one times the derivative of the second one. That would give us 12x to the fifth for our derivative. But if we use the power rule and we multiply first, we know that when we multiply powers with the same base, we keep the base and add the exponents. And then we definitely know from yesterday that h prime at x should be 7x to the sixth. Definitely not 12x to the fifth, so this is definitely not the power rule. Okay? It was actually Leibniz who came up with the product rule for two functions. So he said if h at x is equal to one function f at x times another function g at x, then h prime at x is equal to the derivative of that first function times the second function plus that first function times the derivative of the second function. And write small, we're going to do this proof here, but you're going to have to write small to fit it all in. And we'll start. So if we start from first principles, we can say that h prime at x is equal to the limit as h approaches 0 of, so here's our function h at x. So it would be, we could say h at x plus h, but we know that h at x plus h would just be f at x plus h times g at x plus h. So I'm going to start there just to save space as well. So the limit as h approaches 0 of f at x plus h times g at x plus h minus, that would be h at x, but we know h at x is f at x times g at x all over h. Okay, and then one trick in a mathematician's toolbox, we've talked about multiplying by 1 as something that can work out for us, and we've used that when we've been evaluating limits with our conjugate. But also adding 0 can be a really smart thing to do as well, and especially if we add 0 in a smart way. So that's what Leibniz did. He said we can add 0 by first subtracting f at x plus h times g at x, and then adding f at x plus h times g at x. So in the middle here, he's basically, with this part here, just added 0. And then we still have the minus f at x, g at x. Oops, don't need that extra bracket there, all over h. And then what he did was he divided up the limit. He noticed that we can use properties of limits effectively. This is a common denominator, so we could divide it up if we wanted to into 4 different fractions all over h. But we're going to divide it up into 2 for now. So we're going to do the limit as h approaches 0 of f at x plus h, g at x plus h, minus f at x plus h, g at x, all over h. And then we're going to add the limit as h approaches 0 of these two, so f at x plus h, g at x, minus f at x, g at x, over h. So these two statements are, again, equivalent, just written differently. We've broken the limit up into 2 limits. Now, within the first limit here, I'm going to common factor f at x plus h out of the terms in this first part of the numerator, and I'll get g at x plus h minus g at x, and then that's still all over h. Similar idea here, but my common factor here is g at x. And if I factor g at x out of the terms in the numerator, I'm going to get f at x plus h minus f at x. And that's still all over h. Then Leibniz had a smart idea too. If we have the limit of a function times another function, we can divide that up into the multiplication of limits. So we can have the limit as h approaches 0 of f at x plus h times the limit as h approaches 0 of g at x plus h minus g at x over h. So if we multiply those two limits together, we get back to here. Notice that if you multiply this by this whole thing, you get back what you started with. Over here, Leibniz thought, well, g at x doesn't depend on h, so it can come out front of the limit. So we can have g at x times the limit as h approaches 0 of f at x plus h minus f at x over h. So then Leibniz surveyed what he had. And he said, well, the limit as h approaches 0 of f at x plus h is just f at x, because I can let h approach 0. Here, the limit as h approaches 0 of g at x plus h minus g at x all over h is the definition from first principles of g prime at x. Over here we have g at x. And then this is the definition of f prime at x from first principles. And then he just put it in a different order that he felt was easier to memorize. So we put this term first with the f prime at x first. And then this term second. And then when people remember the product rule, they think of it this way. So this is the derivative of the first function times the second function plus the first function times the derivative of the second function. So that's actually the product rule. So if you're multiplying two functions, it's the derivative of the first times the second plus the first times the derivative of the second. So if we go back up here to this question, and we wanted to do it using the product rule that we know is correct, h prime at x is the derivative of the first one, which is 4x cubed, times the second, which is x cubed, plus the first function, which is x to the fourth, times the derivative of the second one, which is 3x squared. And we can see that that would be 4x to the 6th plus 3x to the 6th, or 7x to the 6th. So our answers agree, doing it using the power rule, and then doing it using the product rule. So obviously in this case, it would be easier to multiply these functions together first and then use the power rule to take the derivative rather than use the product rule. But in either case, you'll get the same answer. Oh, I left you space. Okay, so here's our first example. So differentiate using the product rule, so that means find the derivative. So when I set these up, and this will be really helpful as we get harder and harder products to differentiate later on when we learn the chain rule. But I always like to keep things organized, so I do the first function, second function, and then we talk about the function and its derivative. So F stands for function and D stands for derivative. So the first function is 3x squared minus 1, and its derivative is 6x. And the second function is x squared plus 8, and its derivative is 2x. So if I apply the product rule, f prime at x is the derivative of the first one. So derivative of the first one times the second one. So those go together, times the second. Plus the first function times the derivative of the second one. So you see we're going to be multiplying these two together. But because we're multiplying them together, and it doesn't matter what order you multiply things in, I always like to put the monomial term first. So we've got the derivative of the first times the second plus the first times the derivative of the second. Now, that's probably not going to be the answer in the back of the textbook. We're probably going to have to reduce it somehow. So one thing we could do is expand it. So in this case, I would get 6x cubed plus 48x plus 6x cubed minus 2x. And then that's going to give us 12x cubed plus 46x. And that could be the answer in the textbook. That could well be it. If you're asked for something called simplified factored form, so only do this when you're asked to do it, but if you're asked for simplified factored form, that means that you look for any common factors or trinomial factors, whatever it happens to be. In this case, we do have a common factor of 2x, and if you common factor 2x out, you're going to get 6x squared plus 23. And that would be the simplified factored form version of the answer. So yes, these are equivalent. If you're not asked for simplified factored form, you don't need to do it because it requires factoring in more algebra. And you could leave your answer as 12x cubed plus 46x. If you are asked for simplified factored form, then do look for factoring, and we'll kind of go through that as we go through the lesson. Okay, so B. So we still want to set up our first function, our second function, and its derivative. So my first function is x squared minus 3x. Its derivative is 2x minus 3 using the power rule. My second function is x to the 5th plus 2, and its derivative is 5x to the 4th. So if I was finding h prime at x, it's the derivative of the first times the second. Both of those are binomials, so it doesn't matter which one I put first. Plus the first times the derivative of the second. Okay, so that crisscross is going to be all the time here. But we do have a monomial term, so I'm going to put that one first, since multiplication is associative and it doesn't matter which one you write down first when you're multiplying them together. All right, so again, doesn't look like that's going to be the answer in the back of the book, so we could expand here using FOIL and just the distributive property here. So that's going to give me 2x to the 6th plus 4x minus 3x to the 5th minus 6 plus 5x to the 6th minus 15x to the 5th. And then we can look for any like terms. So we've got x to the 6th and x to the 6th here, giving us 7x to the 6th minus 3x to the 5th minus 15x to the 5th is minus 18x to the 5th. And then just plus 4x minus 6. So that would be h prime at x. Okay, so the next one, trickier because we have this square root sign. So I would say, well, maybe that's not ready to use the product rule yet. I might want to write it as x to the 1/2 times 2 minus 3x. And we are practicing using the product rule, even though it might be simpler to multiply through and use the power rule. I will talk about that after, but let's use the product rule first, since that's what we are practicing today. So our first function is x to the 1/2, and its derivative, if you remember from the power rule, is 1/2 x to the 1/2 minus 1, which is negative 1/2. And our second function is 2 minus 3x, and its derivative of 2 is 0, derivative of negative 3x is negative 3. So y prime is going to be the derivative of the first times the second. So we have this monomial times a binomial plus the first times the derivative of the second. They're both monomials, so they can multiply together. Okay, so not a pretty derivative. So if we want to pretty it up, we actually could use simplified factored form here. We'll talk about that. Try my best to run you through it, what it would look like here. So here's my first term in the first orange bracket and my second term. We want to look for what's in common. Anytime there's a fraction, you want to factor that out because you want the 2 to end up in the denominator. And then we can compare the x's. So we've got a x to the negative 1/2 and an x to the half. So when we common factor, we take the smallest exponent, if you remember back to grade 10 common factoring. So pretend we were going to divide this whole big chunk by a half x to the negative 1/2. So that's our common factor. Well, obviously the halves would divide out, and so would the x to the negative halves divide out because they're exactly the same. So we're going to get 1 here. So all we'd be left with if we common factor a half x to the negative 1/2 out of the first big chunk is just the 2 minus 3x. Okay? But what happens when we take 3x to the 1/2 and divide by a half x to the negative half? Okay, what happens when we actually do that? So let's think about first 3 divided by a half. Okay, so a half goes into 3 6 times. That's hopefully easy for you guys to see. 3 divided by a half is 6. But when you divide powers, so with the same base, they both have the base x, with the same base, you keep the base x and you subtract the exponent. So I have a half x to the half minus negative half. Okay, so you keep the base x and subtract the exponents a half minus negative a half. So that's going to give you 6x to the half plus half, which is 1, which works out nice. So this is minus 6x. So we get y prime equals, all right, now we want to pretty it up. So what's going to be in the denominator is the 2, and then the x to the negative 1/2 we could move to the denominator and make it x to the positive 1/2 or root x. And in the numerator, I'm just going to have 2 minus 9x. So that looks much prettier than the step above and this step, obviously. And that's called, this is simplified factored form. Okay, so basically when you've done this, this is the calculus right here. To get to this step and this step, that's algebra, okay? And it's algebra at a higher level, but it's still just algebra. So let's see what would happen with this question if we were to use the power rule instead. So I would rewrite root x as x to the 1/2. And if I wanted to use the power rule instead of the product rule, I would distribute first. I would say it's not ready to differentiate yet. And then I would multiply, so I'd get 2x to the half minus 3, but now I'm adding exponents, so x to the, right now it's 1, so 2 over 2 plus 1 over 2. Still not ready to find the derivative. Now I am. So now I've got it in power rule form. So bring down the exponent, a half times 2 is 1, x to the negative half. And then minus 9 over 2, x to the 3 over 2 minus 2 over 2, so reduce the exponent by 1 and you get to the 1/2. Okay, so then again, if we wanted in simplified factored form, which we may not, we may just want to write it as, so we could go down here if they didn't ask us for simplified factored form and write it as y prime equals 1 over root x minus 9 root x over 2. So that's one possibility. But if they want a simplified factored form, we would go up here and we would see that because we have the 2 there, here in the denominator, we want to factor out our half again. And we have our 2 chunks. And we want to factor out x with the smaller exponent, which is negative a half. So think about dividing now x to the negative half by a half x to the negative 1/2. Okay, so that's what we're thinking. We're dividing this chunk by 1/2 x to the negative 1/2. So there's really a 1 up here, and a half goes into 1 twice. And then these just divide out, so you don't have them. Minus, so now we're dividing 9 over 2 x to the half by half x to the negative half. So how many times does a half go into 9 halves? 9 times, okay? And then x to the half minus negative half is x to the 1 again, so we have 2 minus 9x. Again, so 2 minus 9x over that 2 goes to the denominator, root x. So we end up with exactly the same answer using the power rule as we did using the product rule. And we could decide which one we thought was easier. To me, they're both about the same level of difficulty here. All right, next question. So D, we're going to set up our first, second function derivative. So our first function is 2 minus, I'm going to rewrite it right away as x to the 1/2, differentiate, and I get negative 1/2 x to the negative 1/2. Derivative of 2 is 0. Our second function, 4x squared plus 8, derivative is 8x. So we can go for y prime here. So derivative of the first times the second, it's going to be there. We've got our monomial term out front. And then plus the first times the derivative of the second, so 8x times 2 minus x to the 1/2. So it doesn't look very nice right now. If I wanted to look at common factoring here, I'm still going to have a 1/2 exponent. So I might want to expand instead and then survey what I've got. So that's going to give me negative 2x to the negative 1/2 plus, so if I make 2 out of 2, it's going to be 4. Minus 1/2 times 8 is 4x to the negative 1/2 plus 16x here minus 8x to the 2 over 2 plus 1 over 2 is 3 over 2. So here I've got negative 2x to the 3 over 2 minus 4x to the negative 1/2 plus 16x minus 8x to the 3 over 2. These end up being like. So negative 10x to the 3 over 2 minus 4x to the negative 1/2 plus 16x. So now at this point I might want to divide out the, well, let's see what's in common here. There's definitely a negative 2 and an x to the negative 1/2. So if I divide negative 10x to the 3 over 2 by negative 2x to the negative 1/2, I'm going to get 5x to the 3 over 2 minus negative 1 over 2, so 4 over 2. So that's going to be 5x to the 3 over 2 minus negative 1/2. So that's going to be 5x to the 4 over 2, which is 5x squared. And then here I've got minus 4x to the negative 1/2 over negative 2x to the negative 1/2, which is going to give me 2, and that's it, plus 2, because the x is to the negative 1/2 divide out. And then I've got, unfortunately, this is the yucky one, so 16x over negative 2x to the negative 1/2 is going to give me negative 8x to the 2 over 2 minus negative 1 over 2. So that's going to be minus 8x to the 3 over 2 is as best I can do here. And then if I write it out with roots, it's going to be negative 2 times 5x squared plus 2 minus 8 square root of x cubed over root x. And that would be considered simplified factored form. Okay, if I wanted just to leave it, I could, at this step, rewrite it as negative, just with roots. So negative 10x square root of x cubed minus 4 over x to the 1/2 plus 16x, or 4 over root x plus 16x. Okay, if they did not require simplified factored form. All right, next one. Okay, so find the slope of the tangent to that function at that point. So whenever we just want to find the slope of the tangent, we definitely don't have to simplify anything. We can just find the derivative, do the calculus part, and then sub in our x value. In this case, it's going to be x equals 1, which is usually they'll give you a really easy x value to substitute in. So we're still going to do our first, second function derivative here. So our first function is 3x squared plus 2, and its derivative is 6x. Second function is 2x cubed minus 1, and its derivative is 6x squared. So when we find y prime, it's derivative of the first times the second, plus the first times the derivative of the second. So this times this, but we'll put our monomial term out front. And I mean, this one we could definitely simplify, but we don't have to. We can just find y prime at 1 if we feel comfortable substituting in 1 everywhere there's an x. Just be careful when you do it. But we really just want the slope of the tangent at 1, so once we've found the derivative, no matter how messy it is, we can just substitute in 1. So that's going to be 2 minus 1 is 1, plus 6 times 1 times 5. So that gives me y prime at 1 is 36. So therefore, m tangent equals 36. Done. Okay, so when you're finding the slope of the tangent to a function using the product rule, it's easy because you just have to find the messy derivative, substitute in the number. Sometimes simplifying will make it easier to substitute in the number, but if it's straightforward, you don't need to do that. Okay, so if y equals the product of these two functions, find dy by dx. So that's just using Leibniz notation, but it still means derivative of y with respect to x when x is negative 1. So another one of these where we just need to find the derivative and substitute in this time negative 1. So let's have our first function and our second function, function derivative. They're a bit longer this time. Derivative is 3x squared plus 2x. X squared minus x plus 2, derivative would be 2x minus 1. So the derivative is going to be long, but we're just subbing negative 1 in, so it shouldn't be too bad. So derivative of the first times the second, plus the first times the derivative of the second. Really doesn't matter what order you put those two in, but I'll put my binomial first and my trinomial second. And then we want y prime at negative 1 because we want dy by dx at negative 1. Oh, sorry, I should have written Leibniz notation here, guys. So this is dy by dx, and this is what we can say dy by dx at negative 1 just as nicely. So substitute in negative 1 everywhere you see x. And then just be really careful when you're substituting and multiplying. So I'm going to go down to this line here. Okay, so this bracket's going to give me 3 minus 2, which is 1. That's nice. Times this one's going to give me 1 plus 1 is 2 plus 2 is 4. 1 plus 1, yep. Plus, so this one's going to give me negative 2 minus 1, so negative 3. And this one's going to give me negative 1 plus 1, which is 0, times 1. So I've got dy by dx at negative 1, dy by dx at negative 1, 4 minus 3, dy by dx at negative 1 is 1. Awesome. Okay. Next question. Find the equation of the tangent line to the curve. So now we're not just finding the slope, but we want the whole equation of the tangent line. So once we've got the slope at 1, at x equals 1, then we can decide how to find our equation either using scalar vector form, or we can use y equals mx plus b, our choice here. So we do have some roots, so we're probably not going to want to simplify. We're just going to find the messy derivative and substitute in. So let me just write that up here as, okay, hopefully you can see that. And this one is 1 plus x to the half plus 3x. So our first function is 2 minus x to the 1/2, and its derivative is going to be negative 1/2 x to the negative 1/2. Second function is 1 plus x to the half plus 3x, and its derivative is going to be a half x to the negative half plus 3. So y prime is going to be negative 1/2 x to the negative half times 1 plus x to the half plus 3x plus, they're both binomials here, 2 minus x to the half times a half x to the negative half plus 3. So before I substitute in 1, I might want to make it a little easier on myself to substitute in 1, so I might write it as like that, this one like that. 1 plus root x plus 3x plus 2 minus root x, 1 over 2 root x plus 3, and now substitute in 1. So negative 1 over 2 root of 1 times 1 plus root of 1 plus 3 times 1 plus 2 minus root of 1, 1 over 2 root of 1 plus 3. So y prime at 1 is, so that's going to be a negative half times 3, 4, 5 plus 2 minus root 1, so 1 times a half plus 3, so that's going to be 3, 6, 7 over 2. So half plus 3, 3 can be 6 over 2, so 7 over 2. So y prime at 1 is going to be negative 5 over 2 plus 7 over 2, which is just 2 over 2, which is 1. So that works out nicely again. So we know our slope of the tangent is 1. So that's nice. So m is 1. We know the point 1,5, so y equals mx plus b looks like a easy way to do this one then. So 5 equals 1 times 1 plus b. 5 is 1 plus b. B is 4, 4. So therefore, equation of tangent line is y equals x plus 4. All right, find an expression for p prime at x if p at x is the product of 3 functions. So what we're going to do is we're going to let this be our first and this be our second. So if we do first, second function derivative, the derivative of the first we know is f derivative of the first times the second plus the first times the derivative of the second, and the derivative of h at x is just h prime at x. So let's see how that works out when we substitute it in. So the derivative of the first, f prime at x, g at x plus f at x, g prime at x times h at x times the second plus the first times the derivative of the second, so h prime at x times f at x times g at x. We can distribute, so p at x is f prime at x, g at x, h at x, plus f at x, g prime at x, h at x, plus, and let's write these in a different order here, f at x, since multiplication is associative again. So you can see that it's similar to the product rule for 2 functions. Each term, or each function takes turns being the derivative. So that's how you would find the product of three functions. If you had to, not the greatest, but we could do it. So noting the derivative of this one is 6x to the fifth, the derivative of this one is 2x, and the derivative of this one is negative 15x to the fourth. We could find f prime at x following this. So it's derivative of the first times the second times the third plus the first times the derivative of the second times the third plus the first times the second times the derivative of the third. And I wouldn't ask you to simplify it. There's a few things we could simplify like easily, but I'd still leave it as three terms. This is not easily simplified, but when you have two monomial terms, you can definitely multiply them together. And same thing here. We've got two monomial terms again. So we could subtract 15x to the 10th times x to the 6 plus 5. And I would definitely leave it there. And that concludes our lesson on the product rule. Thank you.